This is my custom Galaxy's Edge lightsaber blade controller. It's designed to replace the stock controller to give the blades extra functionality, such as the ability to ignite any color that you want, or to add animated effects like a flicker or a blink. I've made several videos covering the development of this board, going into why I wanted to make it in the first place, some of the issues that have come up during the development process, as well as covering some of the key features that I've added to the blade controller. Starting with this video, and for a few videos more, I want to show you how you could build one of these yourself. I'm going to take you through my process for assembling one of these and installing it. If you've never soldered before, maybe this is a beginning. You can see what's involved, get an idea of if that's something you want to tackle, and then go out and seek out other sources of information about surface mount soldering that maybe better explain the process of surface mount soldering. Perhaps some practice surface mount soldering kits. If you go on eBay and search for something like SMD practice kit, you'll find very inexpensive PCBs that the whole purpose of them is to just solder the components to the board. It's just about getting that practice in, getting a feel for soldering components to a PCB. If you're new to surface mount soldering or soldering in general, expect it to be frustrating at first. That's normal. There's always some issue that crops up, some component that just won't solder correctly. If you're motivated to make one of these and stick with it though, I think you will be successful. To make one of these blade controllers, you're going to need to acquire the PCB and all the little components that have to be soldered to it. I'm going to go over how you can get the PCB and how you can get the components. So we'll begin by going to GitHub, to the blade controller code repository on GitHub. This is where the source code for the firmware that goes on the microcontroller here is stored. When you go to that GitHub repository, the first thing you're going to see is a README file. And the README file contains information about how the blade operates. But if you scroll down a ways, you're going to find a section called Blade Controller PCB. And within that section are links to the different components that you need to buy to then solder onto the board, as well as links to where you can order the PCB itself. In the Blade Controller PCB section, there is a table called the PCB BOM. BOM stands for Bill of Materials. It has two columns. On the left-hand column is the reference designator, and on the right-hand column is the component that corresponds to that designator. What's a reference designator? If you look on the PCB, you will see letter and number combinations like R1, R2, R6, U1. Those are all reference designators. So if we take R1 as an example, and you look on the bill of materials for R1, you will find that it is a 1 kiloohm resistor in a 0402 package. And if you're wondering what a 0402 package is, that's just referring to the dimensions of the component. It's 0.04 inches long by 0.02 inches wide. These are very tiny components. By using the bill of materials, I now know that R1 needs to be a 1 kiloohm resistor in a 0402 package. So I can go online to whatever electronic parts dealer you happen to prefer, look up a 1 kiloohm resistor in a 0402 package, and order, in this case, 7. Because R1 through R7 are all 1 kiloohm resistors in a 0402 package. So here, on this GitHub repository, in the README file here, I have a section labeled PCB versions. And this section talks about the two different versions of the PCB that I've made. What happened is when I first created the PCB, I designed it around one particular voltage regulator for the LEDs. And that voltage regulator went out of stock. And it was out of stock for a very long time. So I searched for an alternative voltage regulator and I found it, and I designed a second version of the PCB using this alternative voltage regulator. I've maintained both versions of the PCB because getting these voltage regulators, for the last couple of years at least, has been kind of difficult. And maybe you could get one, maybe you could get the other. So which version of the PCB you order will depend upon which version of the voltage regulator you can get access to. So we need to look at what's available with those voltage regulators. Under the bill of materials here, under U3, we have the voltage regulator that I've been talking about. We have two versions here, an H version and an L version. And in this bill of materials, I don't just list out the components, but I also provide links to Mouser.com where you can potentially buy these components. Or at the very least, see what the components are, and then compare that to whatever alternative electronics provider you might prefer. So I'm going to use the Mouser links to check what's in stock with those voltage regulators. So I have the LDL11 and the LD39. The LDL is the L version, the LD39 is the H version. So we go into Mouser, and we can see that the L version is in stock. There are 2,500 of them in stock, so I could buy a couple right now, and they cost 88 cents. The H version is also in stock, and wow, it's very in stock right now. It's got almost 100,000 in stock. And this voltage regulator costs $1.16 each. So which one do you pick? Because both are in stock. It really doesn't matter. I originally created these two different versions because parts weren't available when I was in the middle of developing the board. But now the parts are available again, and maybe I need to just ditch one of these completely. I think for the purposes of this video, I'm going to go with the H version. So I've picked my PCB version. I'm going to go with the H version. So I need to order the PCB. Under the PCB versions section of the README file, I have links to the H and L versions. I will click on the H version, which is going to take me to OSHPark. And here at OSHPark, we have, again, if we forgot earlier, we have a bill of materials here and some instructions that should hopefully help you build this thing if you need them. And I can come down to actions here and just click on Order Board. If you don't want to order through OSHPark, you can go and order this through somewhere else. Under Actions, there is a download option, which lets you download the Gerber files that you can then take to any other PCB manufacturer, give it to them, and they can manufacture the board for you. But I'm going to order through OSHPark, so I'm going to click Order Board. And on the order screen here, it says that I'm ordering 3. OSHPark makes boards in 3s, so however many you order, you have to order a multiple of 3. And you can see 3 will cost me $4.35. And I have a few options here on the left-hand side. The only one that I think you need to worry about, and I think you should click on, is this 2-ounce 0.8 millimeter thickness option. With this option, OSHPark will manufacture the PCB at half thickness, 0.8 millimeters, and the copper is going to be made thicker. Normally it's 1 ounce copper, but with the 8 millimeter thickness PCB, we get 2 ounce copper, which means we're going to get copper traces that are going to be more capable of carrying the large amounts of current that we're going to need to drive the LEDs. Stock blade controllers are 1 millimeter thick, and I don't know the copper weight that they're using. It's probably 1 ounce copper. But in any case, I recommend this option if you are ordering the boards through OSHPark. If you're ordering the boards through another manufacturer, I would recommend getting the board made to 1 millimeter thickness to match the thickness of the stock blade controller, just so that it's going to fit a lot better in the blade when you install it. Other than that, I'm all set. That is exactly what I want. I'm just going to hit checkout. During checkout, you have the option for selecting different shipping methods. I'm going to go with the free shipping. You can see they talk about it taking about 5 days to get to you after they're done manufacturing the board. It usually takes from anywhere from a week to 2 weeks for your boards to be manufactured. So expect to have the PCBs in your hand in 2 to 3 weeks when you order through OSHPark. And my order is in, and my PCBs are on the way. If you want to order a lot of these, you may find it cheaper to go with another PCB manufacturer. I have on easyeda.com the blade controller project shared, meaning you can access the schematic and the PCB design of the blade controller. And I have a couple extra PCB designs there that panelize the PCB, meaning it's one PCB, but it's actually 10 of these that you then, when you order them, they come as one big PCB and you can snap off blade controllers when you need them. The reason I've done that is because this PCB has castellated holes. The edge here, those holes are plated through holes that have been cut in half. That requires extra service that PCB manufacturers will often charge extra for. So using a panelized board, I find, reduces the costs of the extra charges incurred by having castellated holes. I just want to point that out, that to anybody who's looking to mass produce these, that option is available, and to be aware of those extra charges. But if you're going through OSHPark, you don't pay for having castellated holes. At the same time, OSHPark doesn't guarantee the castellated holes. They just cut right through them, and whatever happens, happens. In my experience, the castellated holes are fine. You just have to do a little cleanup when your board arrives, and I'll cover that as I assemble one of these. So now I need to order the components to go with the PCB. Back in the GitHub repository, I'm looking at the README file here, and this time I'm going to the PCB Bill of Materials section here, and I need to order all of these components. So let's start with the microcontroller itself. This is the heart of the board. And there are 4 different versions of the microcontroller. Any one will work, whichever one is in stock and the cheapest or available or whatever. Grab that one. So what I'm going to do is I'm going to actually click on all 4 of these links, and we'll take a look at the availability of these components as well as the cost and see what's up. That's in stock. That's barely in stock. I'm going to rule that one out. That's very much in stock, and so is that. So I have 3 options that I'm going to pick from. I'm going to look at the price now. 88 cents, 88 cents, 85 cents. So we could go with the cheaper one if we wanted to. Or what else could we decide which one we want to buy? If we scroll down a little ways and under specifications, look for a packaging section here, and we can see it says reel and cut tape. So that means that these components are going to come in it's like a tape where each microcontroller is sort of tucked into its own little hole, and then tape is put over it, and the whole thing comes as like one big reel. I prefer that just because the other option is usually they arrive loose in a little baggie or a little box with some foam, and it's very easy to lose them. I prefer reel, so reel is probably what I'm going to go with. Let's just see if we have any reel. See, this is a tray version. I don't want the tray version. Tray version here as well. So that very quickly narrows down to my choice of microcontroller. So that's what we're going to go with. Now I know from OSHPark I'm getting 3 boards, so I could just order 3, but I could also order a couple more for spares. For the capacitors and resistors, these things are very tiny, and you're going to lose them. You're going to lose a few when you're assembling your board. It's normal. And ordering an extra 10 or 20 costs you 5 cents maybe. An extra microcontroller is going to cost me almost $1. So do I want to order 6? Do I want to order 5? Do I want to just order 3 and, not worry about it? That is up to you. For me, I am going to go with 5. I'll click on the buy button and I will continue shopping. All right, next up we have the voltage regulator for the microcontroller. We have 2 voltage regulators on the board. Both of them are putting 3.3 volts out. The smaller one, which is located at U2, is designed to provide power to the microcontroller. So it doesn't need to be rated for a very high current, only, 10, 20 milliamps, not really much. But the critical part is the quiescent current. We need something that has less than or equal to 1 microamp of quiescent current. Quiescent current just means this is the amount of power it consumes when it's idling, when it's on but not doing anything. I have 3 options here that I have found that will work. I am going to see what Mouser has available for these 3. And all 3 are in stock, so now I'm going to look at pricing on these. And I can see the first one is 40 cents a pop, 53,000 in stock. I'm going to go with that one. That's pretty easy. Again, I'm going to order 5. I only need 3 because I'm ordering 3 PCBs, but I want spares, so I am going to buy 5. And I will continue shopping. Okay, we have our voltage regulator for the LEDs. Remember, we're going with the H version, so I'm just going to go right ahead and order 5 again. These are probably the most expensive component on the whole thing. You can see they're $1.16 each. So maybe I only order 3. But for now, I'm going to go with 5. Next up, we have L1. This is a 3.3 microhenry inductor. It needs to be an inductor that is capable of handling over 1 amp of current. So I've got these 2 that I found. Are any of these in stock? Yes. What about price? They're the same price. They're practically the same component. I don't know what the difference is. If I went through the data sheet, I'd probably find out, but I'm not going to worry about it. I need only 1 per board. These are about $0.25 each. Maybe I order 6 or 7 or even 10. You don't have to get 10. You could get 5. You could get 3 if you're confident that you're going to have no problem soldering the board. Next, we have a PNP transistor in a SOT23 package. And I need to order 4 of these because they're going to be in positions Q1, Q2, Q3, and Q4. 4 transistors per board. And that first one is in stock and the price is pretty good. I have 4 per board. I'm going to be making 3 boards, so I at minimum need 12. I am going to order, I think, let's say 20. Nice round number. Next we have N-channel MOSFETs. We need to order 3 of these, Q5 through Q7. Again, I have 3 options that I've linked to. You might be able to find others. And everything is very much in stock. And this third one here is the cheapest one, so I'm going to go with that. And 3 per board, so I'm going to need at least 9. I think I'll go with 20 again because, oh, maybe not. Look at that price, $5 for 20. So maybe I just order 10, 12 maybe. And I might go back and adjust my numbers a little bit later. Now, I'll point this out. Life cycle. This is giving you a warning here that this particular component is going to be discontinued in the future. And if you're designing a new PCB, maybe you shouldn't be using this. It's okay. It's fine. Don't worry about it. C1 and C7, these are 330 microfarad electrolytic capacitors with a 2.5 millimeter lead spacing. I'm only linking to 1 option. And these are 32 cents, so I need 2 per board. So I need at least 6. I'll just go with 10. We have 1 microfarad ceramic capacitors. I need to order 2 of these per board. So I need at least 6. You can order 10 here. 10 of those will cost you 19 cents. And you know what? For $1.20, I'm going to actually order 100. And then capacitors C5 and C6. We're doing the H version, so it's a 10 microfarad capacitor. If you're doing the L version, it's only a 1 microfarad capacitor. It's the same capacitor as C2 and C3, so you would only need to double up on the number of capacitors you just added to your cart. Or if you're like me and you just ordered 100 for $1.20, then you're fine. You're all set. But I need to order this H version capacitor, the 10 microfarad ceramic capacitor. And we can see these are going to be a little bit more expensive, whereas 10 would have cost me 17 cents of the old one. Only one of these is costing me 17 cents, so maybe I don't need to order 100, which would cost me $4. But I will order several. In fact, I'm going to actually order 100. I lied. And then we have C4, so we only need to order one of these per board. This is a 100 nanofarad capacitor. Yep, 100 of them will cost you $1, so why not? Ordering a lot of spares is not a bad thing. Again, because when you go to solder this board, you will probably lose a few. They'll fall off or shoot across the room when you try to grab them with tweezers. Buy extras. You will need them. Okay, 2 more to go. We have resistors R1 through R7. So I am buying 7 of these resistors per board. 1 kilo ohm in a 0402 package. 10 cents if I order 1 at a time. But very quickly if I order 10, look at that. It's cheaper to order 10 of these than it is to order 1. In this case, 100 of these is going to cost you 50 cents, so why not? And last but not least, we have this 10 kilo ohm resistor. And it's the same deal. You could order 100 of them at 50 cents. Or not. It's entirely up to you. One thing I want to point out about R8. R8 is present only to discharge one of the large electrolytic capacitors. I found that if you unplugged the blade from the hilt after you extinguished the blade would briefly flash because this capacitor still held a charge, and as the electricity drained from the microcontroller, the electricity in that capacitor will discharge through the LEDs, giving a brief white flash in your blade. And so I added a 10 kilo ohm resistor across that capacitor, and its main purpose is to just discharge that capacitor after you turn it off. The rest of the time that it's in your blade, it's just wasting energy. You could use one of the 1 kilo ohm resistors that you've ordered instead of the 10 kilo ohm resistor, and that would be fine. And maybe that's what I should have put here in the bill of materials. But I want to save every little bit of electricity possible, so I went with a slightly larger value of resistor. But you don't necessarily need that. You could just use one of those 1 kilo ohm resistors that you bought for R1 through R7. So it is up to you. Not having to order this component, it's less of a headache. It's one less thing on the list of materials that you need to order. If you go that way, you're perfectly fine, and you will not run into any problems. But just to be complete with this video, I am going to order some. And again, 50 cents for 100 of these things, so why not? So here we go. Let us take a look at what the cost for all of these components will be. Okay, so all of these components will cost me $32 before shipping. The grand total for all these components will be $40. Maybe $30 if you trim those numbers down a little bit because you don't need so many of those little components. And my order is complete. The grand total is going to be about $42 plus the, let's call it $5 that the PCBs will cost me. So $47 divided by 3. call it $16 in costs per PCB, roughly. It'll be a little bit less than that for you because I bought a few little extras. Now I wait. The components have been ordered. The PCBs have been ordered. It will probably take about a week for the Mauser order to show up. It'll probably take, again, 2 to 3 weeks for the OSHPark PCBs to show up. And then we can continue. About a week has passed since I placed that order that you just saw. And here it is. Here is the box that it comes in. I'm going to suggest that you open this box carefully and reuse it. Use it to hold all of the materials that you're going to need to assemble the blade controller. So you have, one container with all of the stuff you're using in it. That's very handy. That's what I do. So anyways, let's see what we have inside. And here are the materials. Let's take a little look at them. Here we have the 10 microfarad capacitors for the voltage regulator. That is, how many? 100 of them, and that's what it looks like. 3.3 microhenry inductors. So I just will go through the list just to make sure everything is here. 10 kilo ohm resistors, 1 kilo ohm resistors, again that's 100 of them right there. 0.1 microfarad capacitors, those look fine. Now we get into the fun stuff. We have a 2 amp voltage regulator, that's the LD39, that's the H version voltage regulator. And we can just take a quick peek and see what that looks like. I ordered 5 and there they are, right there. This is the reel that I was talking about when I was ordering the microcontroller. So you have this piece of plastic. Each component has its own little pocket to sit inside of, and then we have this clear tape over top of it. And then you just peel that tape back and pop out a component when you need it. Until then, I'm going to put it back inside this anti-static bag here and put that aside. We have our N-channel MOSFETs, and I had 20 of those, and that's what that looks like. These are the bipolar transistors, those are the PNP transistors. And then we have 2 really big, interesting looking bags. In here we have our microcontroller, our ATtiny 1606, and this is a bag of the 3.3 volt voltage regulators for the microcontroller. Very curious how this voltage regulator is in this big package here, but the voltage regulator for the LEDs comes in just this little simple anti-static Mylar bag. Why? I don't know. Let's see what it looks like. So this little card here is just something that indicates the moisture level that's inside the bag, and you can see that these dots here are different colors, and if this starts to turn red, then too much moisture got in. It's kind of interesting. 5 of those voltage regulators, that tiny little strip there, all of this has gone into protecting them. And we'll go ahead and take a look at what the, oh my gosh, there we go, we'll fix the exposure. Fix the exposure there, and let's take a look at the microcontrollers to see what that looks like. There are the microcontrollers for the blade controller. That's the heart of the whole thing right there. And we've got 5 of those, or 6. Did I order 6? I may have adjusted it to 6. Oh, that's a mistake. Look at that. I've got 6 here. I ordered 5. Awesome. 1 free microcontroller for me. So I'll package all of this back up, and I'm going to put it all back in the box, and I'll put this aside. This is where all of my project materials for this will go. So I probably have another week of waiting for the PCBs to arrive. But for you, through the magic of editing, it'll happen in a moment. A letter has arrived from OSHPark. And here are our PCBs. And those look pretty good. Now, we're going to have to do some prep work on these. But before we do that, I'm going to put the PCBs back. I'm going to put them in a box along with the materials for the blade controller because, as I said earlier, keep that box around. Keep all of your stuff in there so that way you know where it is so you don't lose it. So you don't need to go searching for a resistor or a PCB or a microcontroller or whatever. You know exactly where it is at all times. The materials are in hand. We are ready to start assembling a blade controller. Now here is one of these PCBs from OSHPark, and the first thing you're going to notice is it's got all these little points around the PCB. It's just a product of how OSHPark manufactures PCBs, and we need to trim them so that way they're not in the way. Otherwise the board might not fit inside the blade when you go to install it. I like to deal with these in two steps. The first step is I have some side cutters here, and I will just clip off as much as I can of each of these, what I like to call thorns, but there's probably an actual name for them. And I'm not trying to get them flush with the PCB, I'm just trying to remove some of the material here. There's one thorn up by the castellated edges, which is going to be interesting, but there we go. So that's sort of the big material removal step, is using those side cutters. And then I'm going to bring in a file. You can also use sandpaper, anything will work. And just sort of file down or sand down the thorns until you're flush with the edge of the PCB. And you don't have to go all the way. You can see on the left side there's still a little bit of a bump right here. And that's okay. But if you really want to get it flush, go ahead and file that down or sand it down until it's flush with the board. And just go around and do that with all the edges. Okay. Now if we look closely at those castellated holes, you can see there's a bunch of extra copper hanging in there from the bit of the hole that got cut away. What I like to do is I pinch and pull away from the board, like so, to try and get all those little tabs of copper sticking up. And I could just run my finger one way, pinch and grab to get them sticking up again, run it the other way, and just sort of like, bending that little extra flap of copper back and forth, and eventually it's just going to fall off. And the second from the left hole isn't quite perfect. I could leave that as is. Or I could come in here with my tweezers and try to dig that flap and get it up. And now do exactly what I was talking about before. So after a bit of work, the copper flaps are removed. Solder can now get into those holes, which will be important later when it's being installed. And if I look on the edge of the PCB here, I want to make sure I don't have anything making a connection between the holes. And that looks okay. That is how you process the PCB from OSHPark, removing all those little thorns around the PCB and cleaning up the castellated holes. Now we're ready to start actually soldering components to the board. I'm going to start by soldering to the PCB the microcontroller. If you look on the PCB, we have the reference designator U1, which is where the microcontroller is going to go. Our goal is to solder all these exposed pads here that are showing up as gold in color to all of these pads on the underside of the chip, and doing so without shorting any of these pins to each other. It seems like a nearly impossible task, but it's actually going to be pretty easy. However, we can't just solder this with a soldering iron. we have on the bottom of the microcontroller this exposed pad here. This pad needs to be soldered to the PCB, and we have a pad here in the middle of the footprint for U1 for that purpose. There's no way to get a soldering iron between the chip and the PCB to melt the solder. We're going to have to use something else to do this. We're going to use a process called reflow. That is where you take solder, apply it to the PCB, and then place the component over the solder. So you create a kind of sandwich of component, solder, and then PCB, and then heat up that sandwich of material to the point that the solder will reflow. And when the solder goes molten and reflows, it will create a connection with the pad on the bottom of the microcontroller. There are a few different techniques for reflow soldering. You can use an oven, you can use a hot plate. What I'm going to be using is a hot air reflow station. The concept is pretty simple. It's just a device that produces very hot air and it blows it out through a nozzle. You aim the nozzle at the board here and it will heat up the board through the hot air. Here is my setup for doing hot air reflow. I begin by putting a silicone mat on the surface of whatever I'm working on. Silicone is able to withstand the kind of temperatures we'll be dealing with, so it's not going to melt or be damaged by the hot air. The next thing I add is a tile. This is just a random tile from the hardware store. And I have placed on it these self-adhesive vinyl feet. The feet provide an air gap between the tile and the work surface underneath. What I will then do is I will take my PCB that I'm going to be working on and I will tape it to the board using some Captain tape. Captain tape is the brand name for polyamide tape. It's a heat-resistant tape. It's not going to behave in any odd ways while it's being blasted by the hot air. This is so I can poke and prod at the PCB without it moving around while I'm working on it. The reason I'm using a tile and not just working directly on the silicone mat is with the silicone mat, as it's exposed to the temperatures that we're going to be working with, while the silicone won't melt, it'll expand and it'll create a little bubble, and suddenly your PCB that was lying flat is no longer lying flat as it's resting on a bubble now, and that can make soldering the board a little bit more difficult. So that's why I don't solder directly to the mat. And this is a product of just the fact that the PCB is so small, you're going to be heating up all the a large area around the PCB. With larger PCBs you could get away with it just being on the silicone mat, but not for this. That's why I'm using the tile. The device itself, the hot air reflow station, I'll show you that. This is what I use. It is a generic 858D. I bought this on eBay probably around 2019, maybe 2020, and it was maybe $35 at the time. You can find these. They might have a brand name associated with them now, but if you search for 858D, you'll find dozens of different variations of this for sale on eBay, Amazon, and elsewhere. There are some versions that have not only a hot air station, but also a regular soldering iron with it. So if you need both a soldering iron and a hot air station, that might be the way to go. It's very simple. When you turn it on, you set the temperature for the air that you want to come out of the nozzle. This knob here controls the air speed. If you put it up all the way, you might blow your components off the PCB, so maybe you start out at a lower value, and then as the components on the PCB begin to solder to the board, you can maybe increase the temperature, so that way you're getting more heat quickly into the PCB. The nozzle itself is pretty simple. There's a fan in here, and then there's a heating element in this tube here, so air blows across the heating element and out the nozzle. This is an old version. You can tell because the nozzle is wired directly to the box. Newer versions have this where the nozzle can be disconnected, so you can replace it if you break it, like I have already done. But for what it is, for the price that I paid for this, it's a very useful tool. So this is what I'll use when I am doing my hot air reflow soldering. I want to look at a couple of more tools that I'm going to be using during this process. I'm going to be using some tweezers, some fine tip tweezers. You can go with some brand name ones that'll probably cost you like $15, $20. These I got as like a pack of 5 of them. These are just generic labeled ESD 17 curved tweezers. I prefer the curved ones just because it means I can come in at an angle that is more comfortable for me. For solder paste, this is what I'm using. It is a Chipquik SMD 291AX. This is a lead-based solder paste, but they do make a lead-free version as well. So if you prefer a lead-free version, or if because laws in your area require you to use a lead-free version, that is available. Don't worry about that. And I also use this. This is Chipquik SMD 291 Flux. This stuff is the secret sauce of any soldering, really, but especially surface mount soldering. It is magical stuff and well worth the price. When it comes to applying solder paste, there are a few different ways you can go about it. You can buy a stencil, which is just basically a thin piece of steel or maybe polyamide film that has all the pads that you want to solder to cut out of it. So you lay it over your PCB, put on your solder paste, and then sort of, squeegee it or spackle the solder paste across the stencil, filling in the holes, and that leaves you with some perfect squares on your PCB for the solder paste. Or instead of using a stencil, you could apply it by hand, which is what I'm going to do. You could try applying this from the syringe. I have done that before. It works. You will usually put down too much solder paste, and you can clean that up later with a soldering iron and some of that flux. Or you could take some of the solder paste, a little dab of solder flux, mix it up, and then use a toothpick to apply it to all the little pads here on the board. That is the technique that I'm going to use in this video just because I think it's going to be the least difficult. Now I have here a little piece of wax paper and a toothpick, which I'm going to use to mix the solder paste and get it to a consistency that I like before I apply it to the PCB. So I am going to apply an amount of solder paste to the board like that. And I am going to apply just a little bit of extra flux like that. Not too much. And just mix this all up. Alright, now I'm going to apply solder paste to the microcontroller and the bypass capacitor for the microcontroller. So here we go. Now I am applying a large amount of solder paste for the microcontroller purposely because there's a little trick with the microcontroller and the voltage regulator where later on, as the solder paste is reflowed, I'm going to push down on the microcontroller and all the excess solder is going to come squirting out the sides. And that's actually going to work. It's going to squish solder away from where it shouldn't be and keep it where it should be, and it's going to work really nicely. And just a little dab where that capacitor is going to go. It doesn't have to be perfect. Everything will sort itself out. And that's it. That's the solder paste applied. Okay, so now I have my microcontroller and my 100 nanofarad capacitors. I need one of each. So this is just tape that you can peel back. Maybe you can get a fingernail under it somewhere, or get your tweezers and try to get in there like that. Just pull it back enough to expose one. There is our microcontroller. Put these back somewhere safe so you can get them later. And now I need to do the same with these 100 nanofarad capacitors. These are very tiny, but they're also very inexpensive. I bought, I think, 100, so if I lose it here, I can grab another one. It's not a big deal. There we go. And those are our components. And on the away camera, you know, this camera here that's far back, looks like a tiny speck. It's smaller than a grain of rice. But now we'll bring that under the microscope, and this thing will look gigantic. Goes like that. Now for the microcontroller, we need to make sure this gets lined up correctly. Now you can see it, there's a little dot in the top right hand corner, and that matches the dot that's on the PCB. Those two need to be next to each other, so I'm just going to bring it and drop it down. Come on, like so. And I'll give it a little push. And it's not quite aligned. That's okay. It'll align itself. I'm tempted to also leave the capacitor the way it is, but you can see it's a little out of alignment. That looks a little better. Okay. Our components are in place. It's time to break out the hot air reflow station and get to work. So I'm going to turn it on, and it's set at 350 degrees C. The temperature coming out probably isn't 350 degrees C. And certainly by the time it reaches the PCB after traversing a few inches, it's going to be even less than that. This solder paste should melt at like 200 C or 205, 210 C, somewhere around there. But mine, as you can see, is much higher. That's to get heat on the board, and it's to make up for the loss of heat as it's traversing a couple of inches to the PCB. Let's just get into it. Now normally I would be coming over the top of the board, but because the microscope is directly over top of it, I have to come at this from an angle, so the chances of components sliding around on the PCB is actually greater than what it would otherwise normally be. So in the beginning here, my goal here is really just to heat the board up, heat the tile up. This is probably going to take me like a minute or two. If I had preheated the board, which before I put down the paste and the components, I leave everything else as it is and just do what I'm doing now, blast the tile and the PCB with a bunch of hot air. If I had done that, this would take less time, but then you have 2 hot air reflow sessions that you have to go through, so it's up to you which way you want to approach it. Either way would work. And I'm just sort of circling around the board, distributing the heat. I want to get the whole thing nice and warm. And right now I'm heating it up from one side. I'll probably switch over to my other hand to come at it from the other side to try and help, distribute the heat. And I think I can go a little faster now on the fan, on the air. I'm up to about a 5 now on the dial. A little more than halfway. The components aren't really moving, so I'll kick it up a little bit more. The higher the fan speed, the more hot air you're introducing to the board, so the quicker it's going to heat up. And just be patient. This is going to take some time. Especially if you're using this tile method, because you're not just heating up the PCB, you're heating up the tile, which has a massive amount of thermal mass. Which is probably why preheating the tile and the PCB would have been a smart idea, but I have, for whatever reason, not done that. Alright, I'm coming in closer now. I can see some of the solder starting to melt. There it goes, it's reflowing. I'm watching that capacitor. I'm going to switch hands here. See that you can see one side of that capacitor still hasn't flowed yet. It's almost done though. I'm going to bump up the speed a little bit more. There we go. That makes everything happier. Now I'm going to come in here with my tweezers and I'm going to tap the top of the microcontroller here. I see what's happening here. It's out of alignment. I need to bring it into alignment. There we go. You see how I tap it, it jiggles and settles into place? That lets me know that it's aligned. And you notice before when I pushed on it, some solder came out the side and then it got sucked back under. That's because it wasn't aligned correctly. Once I realigned it by pulling it back down a little bit with the tweezers, it settled into place, pushing down on it, squirted out the excess solder. That lets me know it was seated correctly. And you saw the bypass capacitor. You can see how the right-hand pad had a little excess solder on it, and it stood up initially, then settled back down. If it stands straight up, that's referred to as tombstoning. And all you need to do with that is, while it's still warm, just knock it back down with your tweezers. It'll touch the other pad, and once the solder makes a connection with that other side of the capacitor, it'll sort of suck itself into place. So what I'm going to do now is I'm letting my hot air reflow station cool down. It will stop the fan once it reaches about 100 degrees. You can help it by turning the speed dial all the way up to 9 to get it to cool down a little more quickly. And there we go. The hot air reflow station has turned off. I will power it off and remove it for now. Now obviously we have a bunch of excess solder that we need to remove, and that is what I'm going to do. I'm going to first apply some extra flux around the microcontroller like this. And now I'm going to warm up my soldering iron, and then I'm just going to go around the sides and collect all of that excess solder. The flux helps sort of keep things flowing, moving. You can start to see how those 5 pins on each side are suddenly visible now as very separate individual pins, which is very good. We don't want any shorts. Very good. And I'm just going to come in here and tap that capacitor with my iron. I'm going to do this a few times. I'm just trying to get rid of all the excess solder. The excess solder is really not a problem. The only reason to do this is if you're very detail oriented and I want something that looks a little bit more professional. But that's about it. I'm not going to go any further because you really run the risk of messing things up if you play around too much trying to make everything look perfect. All you should really care about is that there's an electrical connection there. If you have too much solder, but it's not creating a short or connecting to a pad next door to the pad that has too much solder on it, usually you should just leave it alone. But I'm setting a bad example. Now at this point you could continue soldering the bottom half of the board. I'm going to recommend you stop at this point and instead clean up the board with a little isopropyl alcohol. And give the thing a quick inspection. Just, look at it with your eyes. Make sure everything looks relatively okay. So what I want to do here, So I just want to make sure I don't have any obvious shorts. I want to make sure everything looks like it's connected. Make sure the microcontroller is flat. Make sure that capacitor is soldered on both sides, which it does appear to be. Everything looks fine here, but there's always a chance that there's something going on underneath that microcontroller. Maybe there is a little tiny sliver of something making a short between two pins that shouldn't be there. The easiest way to make sure that the microcontroller is good and that the soldering job is good is to, at this stage, program it. So that is exactly what I'm going to do right now. This is my custom programmer. This is a USB to serial device. This is a little cable I made, and that is my custom pogo pin adapter, all of which will be covered in the next video. Apply that in like so. Alright, there we go. We are in the programmer header holes. I'm going to hit upload on the Arduino IDE that I have, which has the program for it all ready to go. And it looks like it is programming. Good. So that is the microcontroller successfully programmed. That tells me that the microcontroller is good and that I am ready to continue assembling this board. But in the next video, I'm going to go over how to set up your environment to program this. I'm going to go over how to download the code, how to compile the code, all the tools and libraries and stuff like that that you need to install. I'll also go over the hardware necessary to program it, this USB to serial adapter, this little custom cable that I had to make, this little pogo adapter which interfaces with the programming header on the board, how to make one of those. And once we have the programming environment set up and we have successfully programmed the microcontroller, we can proceed in the third video with finishing the assembly and getting into the installation of the blade controller. Hang in there. It's going to be a long journey, but we will get there. I will see you in the next video.